Hello and welcome. You're going to learn about the graphical representation of data. In this lesson, you will learn how to plot points in the coordinate plane and use the distance and midpoint formulas. Okay, we're going to cover a wide range of topics. Pretty briefly, I might add. Let's just define what a coordinate system is, because we've seen a few of them. There are 3 examples below. We'll name them all. It's a graphical system in mathematics which uses a set of 1 or more values to show the exact position of a point. So on a number line in just 1 dimension, you would just use 1 value, whatever it is, and you can plot it on there. This 2-dimensional coordinate plane, which you'd use 2 numbers, and 3-dimensional coordinate plane, if you can imagine that the z-axis here is sticking out of the page and going into the page while x and y are still where they're at. A rectangular coordinate system is the one that I'm going to be focusing on here, though, and that's pretty much what's going to be happening in these videos, really looking at 2 dimensions. It's also called the Cartesian Plane. It's a coordinate system which the locations of points are given in reference to the axes on a 2-dimensional plane, and the location of any ordered pair is written, the location of any point is written as an ordered pair x, comma, y. So the x-axis is the horizontal real number line right here, and the y-axis is the vertical real number line used right here. And the origin would be another name for the point 0, 0. The 2 axes divide the plane into 4 parts called quadrants. This is quadrant number 1 using positive x and positive y. Quadrant 2 uses negative x and positive y, and we work counterclockwise from here. Quadrant 3 is negative x and negative y, and quadrant 4, these are Roman numerals, by the way, in case you were uncertain. Quadrant 4 is positive x and negative y. If it's in between quadrants, then it's not on a quadrant, it's on an axis. On an axis. It's between quadrants, but it's not on a quadrant if it is. All right, let's do an example. Explain how to plot the ordered pair 3, negative 2, and then plot it on the Cartesian plane provided. Okay, so for 3, negative 2, what we would do is we would start at the origin right here at 0, 0. This is not a point that I'm plotting, I'm just referencing it. And 3, negative 2, 3 comma negative 2 says, I'm going to move 3 units in the x direction and negative 2 units in the y direction. The 3 is positive, and the positive x direction is to the right. So from my 0 value of x, I'm going to go 3 over. 1, 2, 3. I'm going to stop right there. And then for negative 2, whether I'm right here or whether I was right here, I'm going to go 2 units downward because the negative y direction is downward. I'll go 1, 2 downward right there, and boom, this is the point right here at 3, negative 2. That's where it goes on the Cartesian plane. Again, this is x and this is y. Probably not something you don't already know, but when we talk about something such as translation, I'd like for you to at very least understand what negative and positive means and what it means in terms of the relation to a point. So to shift a figure plotted in the rectangular coordinate system by a units to the left and b units upward, so let's say that we were at some point that was x, y, let's say it was right here, and I don't care what the actual values are, but when I go a units to the left and b units to the right, if the original coordinate point was x, y, my new coordinate point, a units to the left, would be subtracting a from x. So if a was like this, like boom, there's a units to the left, well, this x value is now x minus a. And if I wanted to go y units, b units upward, then I would add to my y value. So like that maybe. And then maybe your final point is x minus a, comma, what would that be? Y minus b, or y plus b. I'm not using real numbers in this instance, but if they're saying shifted in some way, you're just taking the numbers and subtracting or adding based on whether you're going up, down, left, or right. Remember, down is subtracting from y, left is subtracting from x. But up is adding to y, and right is adding to x. Okay, a reflection, this is just looking at some transformations just so you're well aware. If you have a point on the graph called x, y, I'm going to show you different ways that you can reflect it across certain axes and certain points here. Let me get one a little more unique. Let's go right here. Okay, here's the original point x, y. If we reflect it across the y-axis, basically what it means is we're using the y-axis as an axis of symmetry, and we are mirroring it across that. So let me kind of get my appropriate color here. If I reflect it across this axis right here, then it's going to bounce across perpendicularly. So I will go, this is 3 units away in the x direction from the y-axis, 1, 2, 3. So this reflects right across here, and x was essentially the number 3, right? So if this number is 3, now this number is negative 3, or negative x, and it's still y units up. So we're at negative x, comma y, after reflecting across the y-axis. Now, even if this was xy over here, yes, we would still reflect it over here, and this would still be negative xy. That doesn't mean this is a negative number. Remember, x could have been a negative number from the beginning. If this number was negative 7, the opposite of negative 7 is now positive 7. So reflecting across the y-axis still changes the sign of the x value. It doesn't make it negative, but it changes its sign. Okay, let's do reflecting across the x-axis. That was xy, so reflecting across the x-axis here would give us, sorry, let me get my line going. Reflect across that axis right there, and my new point is perpendicularly the same distance away from the x-axis on the other side. It would be down here, and we are at x negative y. So again, this y value happens to be negative, but more importantly, I changed the sign. Okay, reflection across the origin. Now, reflection across the origin is a little tricky because you're going to go all the way down to the origin, so it's just a matter of what you had to do to get to the origin itself. And I'm not going to draw the axis of symmetry, but it would be perpendicular to it. So whatever I had to do to get to this origin here, going down 7 and going over 3, looks like if I went down another 7 and over another 3, it would kind of get me to my point that I need to be at. This point is at negative x, negative y. Notice kind of 7 units down, 3 units over. And I know that kind of just looks like a slope thing to you, a line. But in terms of a reflection, it's just more specifically saying that it is hitting it at that point across maybe this line right here. That's its line of symmetry where it reflects. Okay, now we're going to look at representing data graphically, meaning we're given a table or a word problem or something like that, and we're given different ways to represent it. Sound fair? Awesome. We're going to do scatter plot, bar graph, and line graph. What they feature, what they look like, how the advantages, disadvantages. It's really just a visual difference. A scatter plot is basically just a set of points. And they're scattered depending on the amount that you have in the table. That's just how they're going to look. To sketch a scatter plot of paired data given in a table, you represent each pair of values as an ordered pair and plot the resulting points. So sketching a scatter plot of this data, it shows the average length in minutes of professional baseball games in selected years, 92 to 2004, skipping every other year here. You can see as the times kind of change or whatever, they might be going up or down. We'll see when we plot the graph. That's kind of where this thing helps a little bit. Okay, so let's take a look at what's provided for you. You already have these graphs kind of set up with the correct values and the correct categories right here. We're labeling our axes with year and time and minutes. We'll go over to 1992 and up to 170 minutes played, and we're going to get as close as possible to this stuff. 1994, 174. I'm not going to go too slowly through this stuff, just making sure I'm getting as close as possible to these things. 1996, 171. Now that's between 170 and 172. So you can see how it, here, 168, you can see how it's getting less time over time. Oh, and look, it jumped right here, 2000. I don't know if this is actual data. I mean, if this is accurate data. 2002, 172. And 2004, 167, in between 166 and 168. All right, so you have a scatter plot. Literally, the plots are scattered. And it's not showing any sort of correlation of over time, the time is increasing or anything like that. In fact, in baseball right now, they're really trying to reduce the time. So it must have been growing over time quite a bit. Okay, a bar graph. A bar graph for each value of the independent variable in the table, which is the x variable. Draw a vertical bar whose height is the corresponding value in the dependent variable. So here, 1992, what I'm going to do, and I get to use a rectangle tool for this to kind of help myself out, is I'm going to use this 1992 right here, and I'm going to draw a bar, okay? And this bar will grow up to 170, for instance. Boom, like that. So this and this are the same thing. They represent the same information. They're just represented differently. All right, 1994 goes to 174. And these won't look perfect. Go with it. 171. 98, 168. And you might argue this looks better. Depends. I'll kind of show you why you might, or I'll tell you why you might like one over the other, all depending. 2002, 172. And 2004, 167. Okay. So, it just depends on what kind of stuff you're looking for. I mean, I don't necessarily care about all this information below it. These aren't buildings, so I'm not comparing which one's taller or anything like that. But I mean, it just depends on what you want to do with the information. These ones are just clear cut. These are the exact points right here. There's nothing in between, nothing else I'm looking for. Maybe I can do more things with a correlation with this stuff. Or you can also do a line graph of the data, which is what I'm going to do next. I'm going to do it very quickly by doing this. To draw a line graph, plot the points in the table and connect the points with line segments. So you would do exactly as I would have done here in part A, only now you connect them. And how do I do that? Just by, I think that's accurate enough, going from one year to the next. Now literally they're already skipping a year each time, so that's kind of unfortunate, but I'm still going to connect the data that I'm given. So from 92 to 94, boom, here and here, etc. You might not have these points plotted very big. Maybe you just will have these lines right here. Now, I'm not going to connect this line to this one right here or anything like that. That's good enough right there. Now, this one shows different slopes. You can actually literally calculate the slopes, and you might actually end up doing that from time to time and comparing them, seeing if something is progressively the same or very different. It doesn't show a sort of correlation kind of trend line like that. So again, different kind of advantage, different kind of reason you'd be using this as opposed to just this. They all have their uses though, and you'll see them all based on what you're doing with them. Okay, distance on a graph. The distance between 2 points that are directly north, south, east, or west of each other can be measured by counting or by using subtraction. So what does all that mean? Well, if I want to find the distance between, like, say, these 2 points right here, you can tell this is one is x1, y1, and this is x2, y1. Well, the fact that these two y's are the same y value based on the subscript being y1, that means they're the same height, which means these are east and west of each other. Exactly. And if they are, that means that there's a counting measure that you can have. I can take whatever my x1 value is and count all the way up until this x2 value, because these points normally, or these graphs normally have these guys going right here, and you can actually do that counting. If they're too far away, or they're decimals, or you just feel like doing something else, you can also do a subtraction of one versus the other. So the distance between x1 and x2 is x2 minus x1. Actually, it's the absolute value of x2 minus x1, because if you did x1 minus x2, you'd be getting a negative number, and distance is always positive. So if I'm finding the distance between 2 points, one can be west of something and one can be east of something, but the magnitude, the value itself, should be a positive number. If I want to find the difference in distance in height between two things, I just subtract them. And I wouldn't ever say that somebody is negative 4 feet difference in distance from me, in height from me. I could say they're 4 inches or feet shorter. 4 feet's kind of drastic. But yeah, that's kind of all that is there. Okay, what's the distance between the points 5, 2, and 1, 2? So this is one of those examples of same height, but different places on the x-axis. 5, 2 is kind of right here, maybe. Okay, and 1, 2 maybe is right here. All right, so the distance is this value right here. So you could count right here, 1, 2, 3, 4, 5. So between 1 and 5 is 1, 2, 3, 4. It's 4 away. That's the distance. 4 units, I suppose I could say. How else could I do that? Well, because the 2's are the same height, I can take the 5 and subtract 1 from it, and I get 4. Really, it's absolute value because if I did 1 minus 5, I should also be getting 4. The absolute value of negative 4 is 4. Okay, what about 6, 7, and 6, negative 4? Well, if you're talking about two things with the same distance away from each other in the x direction, but they have different heights, such as these two right here or these two right here, now it's a matter of taking your two different y values and subtracting them, y1 minus y2 or y2 minus y1. So 7 and negative 4 here, I would subtract them, and here's where people kind of get confused with regard to the subtraction thing, because now I'm dealing with a negative value right here. So if I do 7 minus negative 4, yes, that will become addition. But that didn't mean that I did not subtract the two values, 7 and negative 4. I still did that. They're 11 away from each other. Does that make sense? Absolutely it does. If this was 6, 7, and this was 6, negative 4, well, this thing first has to go 7 units down to get just to the x-axis, and then it needs to go another 4 units after that to get to negative 4 from the x-axis. So yeah, of course that makes sense that that's 11 apart. And once again, if I did it this way, negative 4 minus 7, absolute value, I'll get the absolute value of negative 11, which is 11. So 11 units would be your final answer there. Again, I could count it based on the graph, or I could just do that subtraction as needed. Okay, distance formula. Now the thing is sometimes points are not exactly north, south, east, and west of each other, and you cannot just do a counting or a subtraction for it. Granted, there will be some counting or subtracting involved, but I can't go across here and say 1, 2, 3, 4. It doesn't quite work that way because our units right here are exactly countable, but anything after that, it doesn't work that way. It doesn't go exactly 1 unit each time, and the slope can change as well. So what do? Well, what you're looking at here are 2 points x1, y1, and x2, y2, and I want to find the distance between them right here. Okay? And in order to do that, let's kind of make a right triangle out of this thing. You can see a right triangle right here, you can see one right here, and I'm highlighting in certain colors and kind of color coding what they all are. If you know the Pythagorean theorem, a squared plus b squared equals c squared, where a and b are the two legs of your right triangle and c is the hypotenuse of the right triangle, there's this relationship in all right triangles that says if you take the sum of your squares of your legs, it'll be equal to the square of the hypotenuse. So d, the distance between, is the equivalent of your hypotenuse in a right triangle, and the distance between your x's and the distance between your y's are the equivalent of the lengths of the legs in your right triangle. So if we did some substitution here, x2 minus x1 took place of a, y2 minus y1 took place of b, and we did a transformation of this thing just to write out a better distance formula, just say the actual distance of instead of distance squared. I'm just going to rearrange the Pythagorean theorem equation a little bit. Instead of a squared plus b squared equals c squared, let's put c squared on the left, a squared plus b squared on the right. Take the square root of both sides, and you get the square root of a squared plus b squared. Now, this does not become a plus b. The square root of a squared plus b squared is not a plus b. It doesn't quite work like that. And if it was true, we would just say a plus b equals c, which is totally against the triangle inequality theorem, but that's okay. Anyway, we have c equals a squared root of a squared plus b squared. Oh, by the way, this is not plus or minus because distance is always positive. Otherwise, it would be. Okay, let's substitute. Let's substitute x2 minus x1 for a. Let's substitute d for c. Let's substitute x2 minus x1 for a. I'm going to go and wrap it in parentheses so I can make sure that I can square it, the entire quantity. And let's substitute y2 minus y1 for b. Now, why am I calling these x2 minus x1 and y2 minus y1? Because those are the differences between x2 and x1, just like we talked about on the previous page. So there you go. D equals the square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared. Now, that's a lot to swallow. That's a lot to memorize. Maybe you already have it memorized and conditioned, but I still argue that there's a better approach of thinking about this by using the Pythagorean theorem. If you can think about it as Pythagorean theorem, if you understand your counting principle of going from here to here, it might not take very long to do, and then you won't end up coming up with that, am I supposed to subtract here or add here? How does that work? Where does the square go? Do I do this one first? As long as you understand what's going on, you're really going to be fine with what it is that you're doing. Let's go and do 2 examples here. I'm going to do one of them just by using the graph, and I'll show you kind of how quickly it is by doing that as long as you have a good understanding of what's actually happening. Find the distance between the 2 points on the graph, and let's go ahead and assume that on the x and y axes, these are going up by 1 each. This is 1, 2, comma 1, 2, 3. So this is 2, 3. And this point is 5, comma, I think 7. Now, I personally am not going to make very big of use of these numbers here, except for asking what's the distance between the numbers 7 and 3, okay, 1, 2, 3, 4, and what's the distance between the 2 points 2 and 5, 1, 2, 3. So there you go. This length is 3, this length is 4, this is a right triangle here, this is our D distance right here, and to solve this, we can just use Pythagorean theorem. I've now created a right triangle. Basically, this is what I did. I created a right triangle, legs, lengths 3 and 4, and this is, I just wrote it. This is going to be 5, by the way. Let's go and solve it. D squared equals 3 squared plus 4 squared. So D squared is 9 plus 16. That's 25. So D equals 5. Okay. Again, I just used Pythagorean theorem through this. I could have called it C. It doesn't matter. We're just trying to find the distance, actually. And they didn't specify which way to do it. Now, it's a lot easier if there's a graph there because you can truly see the visual and you can actually count it. I know the distance between 7 and 3 is 4 anyway. I can just say that subtraction in my head. Now, let's say you didn't have a graph. Let's say you wanted to actually use the distance formula and make it work. Let's do a second example. This one has a negative. Be very careful. Find the distance between the points 6, negative 2, and 3, 7. Okay. I can see that without a graph, that counting measure isn't quite as straightforward, and you really don't want to mess up with your negative. So maybe you do the distance formula this time. I'm going to go ahead and rewrite it one more time for you. But let's make sure that we understand what it is that this thing's saying. Sorry about that. The distance between my x's will be squared. That's like this length right here. The distance between my y's will be squared. That's this length right here. I'm going to add them both up and take the square root of both of them because same thing as Pythagorean theorem. Now, this is basically a straight plugging in scenario. Just make sure that you have properly labeled what x2 and y2 are and what x1 and y1 are. You can choose which one they are. It won't change your answer because we are going to square these values. It makes the value positive in the end anyway. So you can luck out in that sense. Sometimes you can't, though, especially if it's a slope problem. So let's go and substitute. x2 minus x1 would be 3 minus 6. y2 minus y1 would be 7 minus, be careful here, negative 2. Okay? So now we're going for 3 minus 6 is negative 3. 7 minus negative 2 is 9, because it's 7 plus 2. Okay? Negative 3 quantity squared is 9. 9 squared is 81. And you're going to get the square root of 90. Now here you have some options on different things to do as well, because this is not a simplified answer, nor is it rounded to any sort of decimal place. The square root of 90, you should know by, I don't have a calculator right next to me, you should know is in between the numbers 9 and 10, because 9 squared is 81 and 10 squared is 100. So probably around the 9.5 area, maybe a little more. But you can also simplify your radical. The square root of 90, I can divide, no, I can't divide 16, I can divide 18. Let's see, how about we just divide 9 and 10? The square root of 9 is 3, so that gives you 3 root 10. Maybe we look at simplifying radicals later, but this is another appropriate answer. This is a better answer in terms of simplification. Rounded to the nearest tenth, probably around 9.5 is my guess. All right, the midpoint formula. The midpoint formula of a line segment is the point that subdivides the segment into two portions of equal length. And I know you might be going, what did you just say? You're finding the halfway point between 2 points, right? So here are points A and B. The midpoint here, M, is maybe something that you're trying to find, okay? The actual coordinate location, not how far away they are from each other, although that can help you find the halfway point, and I'll kind of show you what I mean by that in a bit. But it's the actual location, the actual coordinate, okay? So even when we come to a formula, of sorts. We're not actually going to, I don't know if I'd call it an equation or formula or anything like that, because it's just the location of the midpoint. To calculate the midpoint of a segment, take the average of the two endpoints' locations. Okay, so why are we saying that? Because if you want to find the halfway point between two things, let's say you took two tests and you wanted to find out that halfway point, that's taking your average, right? Or you take the average, that's the halfway point. 2 points, 2 points, not 3. Remember that. But the average of the 3, I guess, would kind of be the middle of all those as well. You just have to divide by 3. So if I want to find this midpoint right here, I would do like these 2 points right here. The midpoint of AC is this point D right here, and its average is just averaging out your two y values. You know your x value is going to be the same, right? Because it's still on that vertical segment right there. So it's x1, comma, and then you're going to average your two y values. Okay. E, on the other hand, is a horizontal line, so your y value stays the same, but your x values change. So this midpoint here would be averaging your x values and then maintaining that y value. Now this midpoint right here looks like it takes kind of the best of both worlds. In the longer way, though, the height is the equivalent of this y value, and the displacement from x is the equivalent of this x value right here. So I'm going to go ahead and write that one in a second. Oh, I should probably drag this down here, by the way. So D's midpoint is here. E's midpoint is here. There are the locations. All right. So if they're not directly north, south, east, and west of each other, you must take the average of both the x and y coordinates. So I did that. You take the average of the y coordinate here, the x coordinate here. Your midpoint of the points x1, y1, and x2, y2 of segment AB is averaging your x's and averaging your y's. Now, once again, kind of a strange looking formula when all said and done because of all the subscripts and all the different letters and fractions and there's a comma there and parentheses. And we just did distance formula back here, and it had a lot of the same things. And you can confuse yourself. It's entirely possible that you do, straight by memorizing something. So instead of trying to go for a flashcard kind of rote memorization, really try and think of the understanding of what it is that you're doing with this midpoint thing. So instead of thinking of it just as a formula, think of it as a concept. You found the in-between of your two x's. How do you do that? You have to average them. And you know how average works. Same with the y values. And this is a point. It's not a distance. We're not finding out how far away A and M are from each other. And if I found that distance from A to M, how does that help me find the point? Because I can't just count 1, 2, 3. Remember, we can't just do something like that. We'd have to do something else. So using these locations really help. Okay, so let's do an example here. I'll do one just by kind of using the graph, just like last time, one by using more of the graph and one by using the formula a little bit more. So let's go ahead and do that here. I'm going to find the midpoint of segment RS here. And to be honest, I don't really care what these points actually are themselves. Yes, I can use them for the formula, but for the sake of this, all I need to do is find out what the distance is between these 2 points, what the midpoint is between these 2 points, and what the midpoint is between these 2 points. Now, this one might help with you finding the distance. Let's say I call this point T right here. All right. What's the distance between R and T? Well, it's actually countable. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this distance is 10. Now, half of that is 5, which means I can use that 1, 2, 3, 4, 5, and boom, that is the midpoint of these two. I'm not going to write 5 or anything. I just need to make sure that I know what this location is. And this location is -2, 2. Okay, that's one way of finding a midpoint, which is vertical. Again, I can't do it here. I can't do that counting thing here, but if I find this one, and I find this one, then I can use its midpoint, just like that. So, what information do we already know? Well, this isn't so helpful either, because I'm sure you can just look at this and say, hey, I know what the midpoint is. No, the whole point is that this is the same height over here, so at least we know when the y's were averaged, or when we found everything else, we found that this was 2. Okay, the height of this midpoint is 2. And obviously, it looks like this part is 2 as well, but let's find it a different way. Let's use T and S right here. Once again, what's the distance between T and S? 1, 2, 3, 4, 5, 6, 7, 8. Half of that is 4. So count 4 over. 1, 2, 3, 4. Now we're at that point right there. That point is 2, comma, negative 3. But if I go upward from there, you're going to look at the same x-coordinate, which looks to be 2. So your midpoint here is 2, 2. Okay. Seems like maybe a troubling concept, all depending on what you're doing with it. But if you have that diagram there, you can use that visual. Obviously, once again, this was very, very, very helpful to have all these axes, all these crosses right here. But you still got to mathematically show it somehow. Okay, this is a different kind of problem. The midpoint of AB is 2, 1. One endpoint at A is negative 3, negative 5. We're going to find the coordinates of the other endpoint B. This time, you are not finding the midpoint. You have the midpoint. Okay, now I'm going to use it in an equation form, but let me kind of show you a visual of what this looks like, of what you're doing here. So you have your axes, okay? A is at the point negative 3, negative 5. It's down here. The midpoint is at 2, 1. So this is M. Now, B is not in between A and M. B is on the other side of M. Okay? It's the next set of points away. The same distance away as A was from M. So if this is the distance from A to M, well, maybe this is the distance from A to B. You know, B is way out here. So a couple things you can do with this. All right? First of all, you know that it's going to be in the first quadrant. Just from the drawing alone and from the slope and everything else, you know it's going to be in the first quadrant. Second of all, you know that the numbers are going to be greater than 2 and 1. So a couple of those things can help you with your double checking if you feel like you did anything wrong in the end. Okay, now how do you use this in equation form? Because I can just tell you right away, using this as slope, you can see how much you rise and run, and do it again, rise and run, you'll get your answer. But I promised I'd do an equation version of this. So let's go ahead and do that. Now, you have to remember the I'm not saying you have to remember what the formula is, you do. But you have to remember that the formula is not just like numbers, it's coordinate points. This M isn't a number, it's two numbers. M is x1 plus x2 over 2, y1 plus y2 over 2. Okay, remember M is some set of values. This is what they are. And you already have what they are, 2, 1. So if I do substitution for this, they're going to go right here, 2, 1. And I know one x value and one y value. Let's call this x1, y1. And we're going to find x2 and y2. Now you can see where this kind of gets a little confusing because now you're substituting some things in, but not all of them, and they're inside coordinate points, inside parentheses. So you might be asking what to do next. I'm going to show you in a second. Okay. You have to remember that if you calculated this doing it the normal, if you had something like this and trying to find the midpoint, these are two separate values. So what I would do is I would write two separate equations. The 2 is only in reference to your x's. The 1 is only in reference to your y's. So let's go ahead and solve for x2 using only this stuff and the number 2. This one has nothing to do with this information. And this 2 has nothing to do with this information. So I'm going to go ahead and write out an equation that says 2 equals negative 3 plus x sub 2 all over 2. That's just for my x values. For my y values, I have a second equation that says y equals negative 5 plus y sub 2 over 2. So now you're going to solve for x2 and y2 this way using this stuff right here. And you still might be confused because maybe you have trouble with fractions time to time. Well, I have this whole thing divided by 2, so I can multiply both sides by 2. And 2 over 2 is 1, so these guys cancel right here. 2 times 2 over here is 4. So 4 is negative 3 plus x sub 2. Add 3 to both sides. You get x sub 2 equals 7. That is the x value. That's the x coordinate for the point B. Solving for this one right here, once again, multiply by 2 on both sides. And whenever you're doing a midpoint formula thing right here, apparently you're always going to be doing that because you're just averaging 2 points, right? So it looks like you always be multiplying by 2 because it's always being divided by 2. Plus y sub 2. Add 5, you get y sub 2 equals 7. So they're both 7. X sub 2 is 7, y sub 2 is 7. So the point B is at 7, 7. Now, that confirms my speculation that B was in the first quadrant and that these two numbers would be bigger than 2 and 1, just by the drawing alone. That's kind of a good double check. Now, why might you get something different? Well, you might plug in 2 and 1 right here and find a midpoint, or you might accidentally subtract right here, or you might have trouble with this multiplying by 2 business, or you might subtract this 3 instead of adding it. There are a lot of different things. That's why that first drawing was actually pretty good and pretty important. I didn't do anything with the drawing. I still used the formula, but I got to use it still in some capacity. That helped me. Okay, last kind of big thing that we're going to talk about is the equation of a circle. Now, it's still going to use the same concepts that we talked about, but this equation will look a little different just because different letters are being used here. Definition of a circle: it's an enclosed 2D object whose set of points lie equidistant from a single point. The distance from that middle point, called the center, to any point on the circle is called the radius. If the circle is on a graph, to locate any point x, y, we're going to calculate the distance between the center and that point by using the distance formula. So we just use the distance formula. It's been the same thing as the Pythagorean theorem, and I'm going to equate it in that same way as well. So once again, the equation of the circle is defined by the idea that your point, that any point, it doesn't matter if this is xy or if we talk about this xy over here, they're all some sort of, like, they're all different xy values, but they're all the same r away from the center. So no matter what r is, it'll be the same for any part of the circle. So it doesn't matter what point of xy you choose, you should still get the same r. And this center, hk, is always going to be the same center. The only thing that varies is the x and the y, but it shouldn't change your equation itself. So the equation of a circle whose center is at the point hk with the radius r is, well, let's think of distance formula or Pythagorean theorem. The distance between your center point for your x-coordinate h and any point on the circle x will be x minus h. Technically the absolute value of, but because we're using Pythagorean theorem, we're going to square it anyway, so I don't have to use that. And the distance between any y point on the circle and then this k at the center will be y minus k. So once again, if you're looking at something in terms of Pythagorean theorem, a squared plus b squared equals c squared, well, we're going to be doing that same thing. A squared can be x minus h, b squared can be y minus k, and c squared can be r squared. Squared, and then r squared. And voila, that's your equation. That's it. Look kind of strange. But again, this represents something that says that you know how to graph a circle. Well, we might learn this, but you know how to graph a circle, draw a circle based on information that you're given here, based on center, points, and radius. You can use any point on the circle to confirm what the radius is. You can get any other sort of information like that from it. We're going to do some examples. The point 4, -4 lies on a circle whose center is at -2, 3. Find an equation for the circle. It does help to use a graph. It's not necessary. But let's go ahead and make sense of what it is that we're looking at. The point 4, -4 is right here. Now this is a point that's on the circle. I'm going to kind of show you what I mean by that in a moment. And the center is at -2, 3, which is right there. Okay, so if you're going to, not that I'm going to really ask you to draw a circle here, but if you did draw the circle, it would look like this. Because 4, -4 is one of the points on the circle. So is this point here. So is this point here. The question is, what's the distance between this point and this point, or any of these points? Because there is just one number. And if you were able to draw this and use tools and stuff, maybe you could do a count right here, although I doubt that that's on 2 integers. So we're just going to use the, I'd call it Pythagorean theorem, but you know, it's the circle formula. We got to find the distance between the points in the center and the point on this circle right there. It's going to be like that. So you could count. You could go 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. And what do we have? Pythagorean theorem all over again. So r squared is 85. Okay. They're not asking you to find the radius. I could take the square root. I don't know what it is. Again, I know it's more than 9. But they're asking you to find the equation of the circle. And in the equation of the circle, you use the r squared value. So I can find radius, but I'm going to use the number 85 right here. Now, how do you write the equation? Well, you have to remember that this is based on any x, y point, not just the point 4, negative 4. It's any of them. So we get to leave that x and that y very generic. So that's x. Now, notice how it said minus h. So it's going to be minus negative 2 quantity squared plus y minus 3 quantity squared equals r squared, which is 85. So that's the equation. Now I'm going to change that minus and negative to a plus there. But that's the equation of the circle. So as you start to look at some of these things here, you're really going to get used to what these equations look like and where a minus really technically means a plus and a plus means a minus as far as where it's located. Okay, but the distance from it is always subtracting. Even if the number is negative, it might turn into addition, but it's always subtracting to start off. So that's the answer. That's the equation of the circle right there. And as you can probably tell by now, we'll be able to pull information like this negative 2 and the positive 3. We'll be able to pull that as the center, take the square root of 85, you can get the radius. We'll make sure to do an example like that. Like right now. Find the center and radius of the following circle given its equation and sketch the circle. Okay, here's the original equation right here, x squared plus the quantity y plus 3 squared equals 49. Now, if I want to use standard equation of a circle, this looks a little different because x isn't around parentheses. Now, you might ask why it's not. Well, it's because there's no other number that's being added or subtracted to. We can pretend like there is something added or subtracted to it, in which case that number would be 0. It's like x minus 0 squared plus y plus 3. In fact, let's change that plus to a minus a negative, right? If we want to look at this like x minus h squared plus y minus k squared equals r squared, and how about this? 49, that's 7 squared. All of this stuff is going to help for my answer because my center is at the point 0, comma, negative 3. My radius is 7. Now, how do you sketch it? Right? We found this information. How do you sketch a circle? See, I used a circle tool here, and I'm probably going to do it again, but how do you do it with a pencil? Well, first you plot the center. And remember, the center is not a point on the circle. The center only helps you find points on the circle. For instance, I can find 4 points very easily. Where are they? Well, circles equidistant in every direction. And how can I count 7 very simply? Up, down, left, and right, north, south, east, and west. 1, 2, 3, 4, 5, 6, 7. This is a point. It's the highest point in the circle. 1, 2, 3, 4, 5, 6, 7. And 7 over here. And 7 over there. And then you can do a rough sketch. I'm going to do a very, very, very rough sketch right here. But, you can do a rough sketch for your circle like that. Check this out. I'm going to do it this way. Starting from the center, branch out. And you can see how it hits every point, just like that. Okay. Now, all of these are also still 7, right? All of these are 7 away, just in a different way. I doubt any of the other ones actually hit right on integers, like north, south, east, and west, but you do what you got to do. It's a nice sketch there, and I could erase the center if I wanted to at that point. I could even erase those little points too. That's what the circle looks like after you use the equation with it, and it's based on the information that we derived from there. All right, so I hope that this was very exciting. This is what we covered in this section, how to plot points in the Cartesian plane. Again, the x, y, moving over, up, down, left, right, even translation and reflection. How to represent data graphically using scatter plots, bar graphs, and line graphs. Essentially all the same thing, just a different way of looking at it, but still plotting the points using the x, y, determining that. How to use the distance formula to find the distance between the 2 points. Again, that was square root of x2 minus x1 squared plus y2 minus y1 squared. It's Pythagorean theorem in a nutshell. Midpoint formula is average in a nutshell. However, you have to do 2 different sets of values, the x's and the y's, differently. And you can do them all with graphs. And finally, how to find the equation of a circle. Once again, that's using Pythagorean theorem in such a way you have new letters h and k with that. All right, hope you enjoyed it. Fiend!